Hey, hello everyone. My name is Abdur, and I'm a final year PhD student. This is my seventh semester. It's been a long time. I'm here at MSU, and I'm planning to graduate next year. Just to let you know that I'm in the job market right now. And today I'll be presenting on our one of the projects regarding wood-free moisture content prediction. And in this work, we were specifically focusing on texture features and domain adaptation. We try to integrate these two directions of work and try to build a robust moisture content predictor from real-time images. And I will also present this work in the Graduate Research Symposium on next Saturday. So hopefully you will like the presentation. And at the end of the presentation, I would be very happy to have your feedback. So I'm going to cover the problem background, what specific issue we are dealing with here, and what are the specific solutions that are already existing in the literature. Then what are their limitations and how are we going to solve or address their limitations. Then we're going to propose our proposed solution and the outcomes of the proposed method. Finally, we will conclude our results and outcomes and show some future research direction. So moisture content determination in wood chip is very critical for energy efficiency and product quality. So what does that mean? So energy efficiency means that if there is high moisture content or high amount of water in wood chips, the factories or mills would require high amount of energy to evaporate the water from the wood chips. So this is a waste of money and waste of time and the waste in the overall supply chain process. Then the second one is the product quality of the biofuel or biomass based factories. They depend on the specific range of moisture content. So if the moisture content is less than that specific range, they need to figure out a way to make the moisture content within the range. So therefore, determining the moisture content in a quick and reliable manner is very important. If we look into this supply chain graphic, we will see that most of the wood chips come from the forest and the lumber mills, and they are sent to the wood chip processing mill. And you might see that this kind of sign is shown in different part of the figure. And these are the points where wood chip moisture content are required to determine. So wood chip processing mills send their processed wood chip to different factories, let's say biorefinery or pulp and paper factory or biofuel factories. So as you can see, in different stages of the supply chain, moisture content measurement is required. But the existing traditional method that is used in current industry is oven drying, which requires around 24 hours of time. And it is also non-invasive. It is an invasive method or destructive method. That means it would alter the physical property of wood chip. Then it basically creates the bottleneck in the supply chain, and eventually it makes the production inefficient. So what our solution is going to do is that we're going to reduce this processing time from 24 hours to even seconds or minutes. Then we are going to propose a non-invasive way of doing determining the moisture content, and eventually we will remove the bottleneck and make the production system efficient. Next, there is another challenge here, which is the challenge of heterogeneity. Heterogeneity means that the distribution of the data could be different in different scenarios. The heterogeneous distribution could come from the type of the species of plant, the cutting method of the wood chip, or the source of the wood chip, then color, shapes. There are many different variables that could alter the properties of the wood chip. As you can see, the first column is showing the images of wood chip from source 1. Similarly, from source 2 and source 3 can be also seen here. And there is a very slight difference in the moisture in the visual thing, you can see here in terms of the moisture content. Let's say the top row shows the dry, medium, and second row shows the medium, and third row shows the wet images. So if we look into the literature, only very few of them can actually address the issue of instantaneous prediction. For example, a near infrared spectroscopy based method, they can predict the moisture content instantaneously, but they have a limitation that they provide only surface moisture measure. They cannot predict the moisture content of the wood chips that are below the surface. Then again, there is another method for time domain reflectometry. It also comes with another limitation. The only method that can address heterogeneity issue is the traditional gravimetric approach, which is also known as the oven drying approach. But this again takes huge amount of time. So our proposed method is based on texture, feature, and domain adaptation that can handle both of these two challenges. So overall, our objective and contribution sums up here. We want to develop a method that can predict moisture content instantaneously and in a non-invasive and cost-efficient manner. For that, our solution is the texture features and machine learning methods. And the second challenge is the heterogeneity. We want to adapt the method to different heterogeneous wood chips using unsupervised domain adaptation. If we look into the data acquisition part, this is the setup on the left side. As you can see, we have a industrial grade camera. With this, we captured the image of wood chip that is shown in the right side figure. And we use two ring-shaped lights to ensure uniform lighting conditions. Now, in the texture feature extraction, we have considered 5 different texture features as listed on the left side here. But for demonstration, I will only look into the heraldic texture feature. And at first, we convert the RGB image to grayscale image like this. And let's consider this small portion as an example. If we consider this small portion and represent the pixel values with 3 different gray levels, let's say 1, 2, and 3. This is the representation that we have. And in the next stage, we would consider trying different constructing an adjacency matrix with different directions. For example, if we take direction 0, then we will try to see if there is similar values in the x-axis. So as you can see here, 2 and 2 is on the. We have number of 2 and 2. This pair is number of only ones. That's why we consider this index 2 and this index 2 to be value to have the value of 1. And again, we have 3, 2, 3, 2 twice. That's why we say 3 and 2. This part is equal. Similarly, we would create the matrix in 45 degree, 90, and 135 degree directions. And finally, we would create an average matrix. We call this matrix gray level cooccurrence matrix. And after that, we take the probability representation using the normalization of the values. Then we represent this matrix as G. And from here, this matrix will be used to calculate some texture features, what we call the heraldic texture features. And for an example, we can calculate the angular second moment, which can be calculated by taking the square of the pixel values. And similarly, we can calculate the rest of the heraldic features. We have total of 28 features in the heraldic texture feature class. And as I already mentioned, we calculated 5 different types of texture features with 3 different wood chip sources. Then we have considered 12 different machine learning models that includes traditional machine learning models like decision tree, then k nearest neighbor. We also have some ensemble model such as gradient boosting, extra tree, something like that. And also we have voting classifier, which can take the best 3 models and combine their predictions in a voting manner. For training, we have considered K4 cross validation, and we have evaluated the model from 4 perspectives using 4 different evaluation metrics. And this table basically shows the results that we got from training and testing on source 1. And as you can see that we are getting an accuracy of 95%, which is pretty high compared to the existing literature. Then again, this was tested on source 1 only. So the next table we have, this table represents the average values of source 1, source 2, source 3, and different types of texture features as well. So earlier we had 95%, but now we're showing what are the performances across other texture features. As you can see that only heraldic features showed the best performance compared to the other features. But we also tried to combine the features together to see if the performance increases or not. And have found that the combined features actually show the best results. Now, what happens if we change the source of the training data and testing data? As you can see here, our training and test set were similar and we achieved a 95% accuracy. But in the next thing we want to try, we want to train the model with source 2 wood chips, but we want to test that on source 1. And as you can see that we have a pretty huge drop in terms of accuracy. From 95, we're getting 55 and 32. So the solution here is that we propose domain adaptation method that can adapt source 1 to source 2 and source 2 to source 3, something like that. So here is a very simple representation how domain adaptation model works. Let's say you have images of dog and cat in real life image, but you also have another domain of image, just clip art or icons. So you train your model with real image, but you want to predict the model or evaluate the model on this clip art. So you have source domain which has labels, but your target domain doesn't have any label. So you try to extract common features. Let's say the dog in this image and the dog in this image might have some common features. The model try to extract those features. And this feature extractor works as a generator, and this discriminator works as a discriminator. And in this adversarial manner, they try to identify the domain invariant features. That means the common features between those two domains. And eventually, we would have a classifier that can predict pretty good accuracy on the target domain. We adapt this idea to our method. And as you can see here, we have wood chips from 2 different sources. We have a feature extractor. We extract the domain invariant feature. And eventually, we try to predict the level of the target data. And in this method, we would have an adversarial loss that would be calculated from the domain discriminator. We would have a classification loss that would be calculated from the label classifier, and we would combine them with a parameter lambda, and that would give us the total loss of the model. And this table shows the performance. For example, earlier we were having 54% accuracy. If we train and test on, let's say, training on source 1 and testing on source 2, we get an accuracy of 54. But if we use the domain adaptation method that we propose, we get an accuracy of 79%. So these results definitely shows a great improvement if we use the domain adaptation method. So I would like to conclude that texture feature has high potential in wood chip moisture content prediction because it can detect those tiny and slight changes in the texture. Then the combined features altogether with the voting classifier can achieve high accuracy as much as 95%. And the data heterogeneity problem in wood chip or from different sources can be solved using domain adaptation. But this is, as you can see, the accuracy is up to maximum up to 80% or 66. So there is still room for improvement. So that's why we say that this problem can be solved to some extent. The future research direction include using multi-source domain adaptation, because as you have seen that we have 3 sources of wood chip, we can combine 2 of them and try testing on other. So we can use multi-source domain adaptation. Second one is that we can use neural architecture search to automatically generate or optimize the neural architecture for the extractor. And finally, we can deploy the trained model on the smartphone or any web app so that this can be used in industry, and this would be very helpful for determining the moisture content in the industrial scenario. Finally, we would like to acknowledge the funding support from USDA, and I thank all of you for listening to my presentation. Thank you. If you have any questions.